Hello again, this is Professor Roman. Let us continue the lecture series Transition to Advanced Mathematics. We just finished our discussion of sets and multisets. Now I want to talk about another proof technique called mathematical induction. It's a very powerful proof technique, but also rather specialized. It works in certain situations, not in others. But when it does work, it's very powerful, and so it's an extremely important proof technique. We do need, however, to talk about a few things before we take a look at induction per se. First is summation notation. It's quite common in mathematics and applications to deal with sums of various kinds. And for this reason, a special notation has been developed called summation notation. Here's a simple example. If we wanted to sum the integers from 1 to 5, already a little mistake there, then this is that sum, and it would be denoted in summation notation by a capital sigma, which stands for sum, and an index is chosen, something called an index of summation. I equals 1, and there's a 5 up there, and there's I here. So what you do is, it's analogous really to a notation we've already seen. The union, I goes from 1 to 5 of AI, is this union. Here we take the index of summation and we let it range from the lower limit 1 to the upper limit 5, and we replace this I by these values and then sum. So we get this. Any letter that you want for the index that you can use for the index of summation doesn't matter, as long as you're consistent and as long as it's not being used for something else at the same time. So this would be the sum of the first 100 positive integers. You can use the index of summation I or J or K or N, whatever you want. As I said, the starting value for the index is called the lower limit of the summation, and the ending value is called the upper limit. If the upper limit is less than the lower limit, then by convention the sum is 0. So for example, the sum on I, where I ranges from 5 to 4, would be 0. So in general, to evaluate an expression like this is a sum. I goes from L to U, lower to upper, of P of I, where P of I is some expression, algebraic expression. We just substitute consecutive integers starting with L, so P of L, then P of L plus 1, all the way up to P of U, and add them up. And here are several examples that should cement this idea for you. Sum I goes from 1 to 5 of 3i squared is 3 1 squared plus 3 times 2 squared plus 3 times 3 squared plus 3 times 4 squared plus 3 times 5 squared. Sum I ranges from -1 to 1 of 1 over the quantity k plus 5 times quantity k plus 6. We just replace k by -1, then by 0, then by 1, and we get these three terms, which can then be simplified. Sum k goes from -m to m of k to the n, -m to the n, -m plus 1 to the n. Eventually you'll hit 0, and then it'll be 1 to the n up to n minus 1 to the n plus m to the n. Now I guess I should have said that m is greater than or equal to 0, otherwise this would be 0. Here's a sum, I goes from 1 to 5 of 3. So in this case, 3 does not, I'm sorry, k goes from 1 to 5 of 3. 3 does not involve k. So as we change k from 1 to 5, we're always going to get 3. So 3 plus 3 plus 3 plus 3 plus 3, 5 of them, because there are 5 values for the index of summation. The sum of the first 5 even integers looks like this. Here it is in summation notation. The sum of the first n positive perfect squares looks like this, or in summation notation like this. There's a corresponding product notation. It's analogous to the summation notation. Use a capital pi. Otherwise it looks the same, but now instead of adding, you multiply. So you do the same substitution procedure. Substitute I equals 1, then 2 up to 5, but each of the individual substitutions are multiplied together. Okay, now, the main topic of this chapter, as I said, is mathematical induction. We're going to need summation notation for the examples and the exercises, which is why I covered it. And you'll be using this notation for the rest of your mathematical career. It's very, very common. But in order to justify mathematical induction, and you now know that everything must be justified, we're going to need to look a little more closely at the natural numbers. We have informally defined the natural numbers as follows. 0 is the empty set, 1 is the set containing 0, 2 is the set containing 0 and 1, 3 is the set containing 0, 1, and 2, and so on. Well, that's not a formal definition. I can't say, here are the first 4 natural numbers, you get the pattern, here's what the pattern is, we're done. We need to be more careful than that. Some time ago in the chapter on sets, I gave you the formal versions of the Zermelo-Frankel axioms. And at that time, I defined for you the notion of the successor of a set. So if X is a set, the successor of X is this set, X union the set containing X. In words, you take the set X and you throw in another element, and the element you throw in is X itself. X does not belong to X. That's not allowed under the axiom of regularity, but there's no reason why you can't take X and add X as a new element. That doesn't violate the axiom of regularity because S of X is a new set. It's not X, so X can belong to S of X. This set is guaranteed to exist by the axioms of set theory. The axiom of pair will give you this set, and the axiom of union will give you this set. Also, I mentioned that any set I that is closed under the taking of successors, in other words, oops, I've got some inconsistency in the letters here. If A is in I, that implies that S of A is in I, is called an inductive set. And we saw that the natural numbers formed an inductive set informally. We didn't prove this. Informally, it forms an inductive set that contains the empty set. I'm going to revise that just a teensy-weensy bit. Most of the books I looked at recently define an inductive set as a set that's closed under a successor, but also that must contain the empty set as an element. So I want to be as consistent as I can with the majority of other books. Not all of them require that. So I'm going to make that alteration. So any set I for which the empty set is an element of I and that is closed under the taking of successors is called an inductive set. I apologize for making this change. It's not really cool to do that, but it's a minor change, and so it shouldn't be too upsetting. Now our intuitive definition of the natural numbers, we haven't made a formal definition, indicated by these first few definitions, can be summarized in this way. 0 equals the empty set is a natural number. If n is a natural number, then so is its successor. In fact, the successor of n is what we're calling n plus 1. But also, we don't want anything else to be part of the natural numbers that we can't get from the empty set by applying successive successors, okay, multiple successors, finite number of successors. So that's what paragraph 3 here is. It's called the limiting clause. No set is a natural number unless it can be obtained from 1 by a finite number of applications of 2, taking successors. So this is called the limiting clause because it prevents or limits sets from being included in n undesirable type sets. Now, how do we make this intuitive definition more formal? All we need to do is to observe that according to our intuitive definition, not only is n an inductive set, if it contains little n, it contains the successor of little n, and it contains the empty set, but any inductive set must contain the natural numbers. If I is inductive, then I contains the empty set as an element. You know, the word contain can mean sometimes subset as well as element, so I have to be careful. We're talking here about element. The empty set's a subset of every set, so there would be no point in even bothering to say that in the definition of inductive. When I say the empty set is contained in I mean it's a member of I, an element of I. Okay. And it's closed under successors. Then it's going to contain 0, then it's going to contain 1, and therefore 2, and therefore 3, and so on. It'll contain all the natural numbers. Now, again, I want to emphasize, we are speaking informally still, intuitively. It seems intuitively clear that an inductive set, since it contains the empty set, which is 0, is going to have to contain 1, 2, 3, and so on, therefore all natural numbers. So put another way, it does seem that n is the smallest inductive set. but we have to justify that that exists. And then we could take this as the formal definition of the natural numbers. It's an inductive set that's contained in any other inductive set. And therefore it must be the smallest inductive set. That's equivalent. So we'd like to officially define N to be this set, the set of all sets X, such that X is in I for all inductive sets I. But we've learned a lesson already, I hope, from Russell's paradox, that just because you throw down a bunch of symbols and put curly braces around them doesn't make a set necessarily. So we need to justify that this is in fact a set. One way to do that is to observe that this is a class and then go from there. And I thought about giving you that argument, but then I thought, well, classes, proper classes, aren't really an official part of this course. They come up occasionally. I explained why, but I would just as soon limit the exposure here to classes, because there are other ways to deal with the paradoxes that don't involve classes, using hierarchies of sets and so on. So I don't want to put too much emphasis on that. So here's a way around this issue. The issue is really right here. X is ranging over all sets, and the collection of all sets is not a set. So it's a class, a proper class. So we're ranging over a proper class here. So we need to be a little careful. But here's what we can do that will avoid any ambiguity issues. Everything will come out just fine. We know from the axiom of infinity that there exists an inductive set. That's what the axiom says precisely. It says there's a set that contains the empty set as an element and is closed under successors. It doesn't limit the set in any other way. So there could be other elements in there that don't come from the empty set by taking successors. We don't know, we don't care. There is an inductive set, and I'll call it A. There could be more than one, but there's at least one. Now let's look at this, which is almost the same as this, but the universe has been cut down from the class of all sets to the set A. Now X ranges over a set. The rest is the same. And this can be shown to exist using the axiom of separation. We separate out certain elements of A based on this property, that they belong to all inductive sets. So this set exists, A prime. Now, we'd like to define the natural numbers as this set, but there's a huge potential problem. And I would urge you to stop the video and think about this and see if you can spot the potential problem. Here's what it is. The choice of inductive set was arbitrary. We know one exists, but there may be many, as far as we know. And so if we select a different inductive set, call it B, how do we know that A prime and B prime, which looks just like A prime, but here this is B, are the same? If they're not the same, then we have a problem of ambiguity, because different inductive sets will lead to different sets that we'd like to call the natural numbers. We got confusion, chaos, cannot be. In order, let me put it to you this way. We'd like to say that the natural numbers consists of the set of all x in A for which x lies in every inductive set. So this depends on A. And a different A, if it gives a different set here, we have a problem. So what we have to show, because A is an arbitrary inductive set, there's no way to single out a particular inductive set because the axiom of infinity just tells us there is one. It doesn't tell us anything about it. So where we stand is that if A and B are inductive sets, we have to show these two sets, A prime and B prime, are the same. And frankly, that's one or two lines. Using the definition of equality of sets, the axiom of extensionality. And I'm going to let you think about that. As I said, it's a very short, very simple proof. Use your skills now. The first skill you have is go over the definition of what it means to say these two are equal. Apply the definition. So now we have removed any possible ambiguity, and we can make the following formal definition for the natural numbers. The set N of natural numbers is defined to be this set, the set of all elements of A, x in A, such that x belongs to every inductive set. And I say where A is any inductive set. There is no ambiguity here. I might choose one inductive set, you might choose another, it doesn't matter. This set will come out the same in both cases, so we can call it the natural numbers. So this is the formal definition, and that's often expressed simply by saying that the natural numbers form the smallest inductive set. Is that a little thing I gotta fix? Okay, so we've covered the summation notation. We've formally defined the natural numbers. And now we can discuss mathematical induction, and we can justify induction as a valid proof technique. And that's going to require using the formal definition of the natural numbers. All right, now we have taken care of the preliminaries, the summation notation, also given a formal definition of the natural numbers. We can proceed to the business of this chapter. Mathematical induction, or simply induction, is, as I mentioned, a very special type of proof technique. It's used to prove certain types of mathematical statements, including many that involve summations, as we will see. When it works, it's a very powerful technique. When it doesn't work, well, then it doesn't work. The idea behind mathematical induction is that if we have a sequence of propositions, and I'm denoting them by P of n, there's one proposition for each natural number n. And if we can prove two things, P of 0 holds, that's the first proposition when n equals 0, and these conditionals hold for all natural numbers n, P of n implies P of n plus 1, then we can conclude that P of n holds for all natural numbers n. To justify this informally, we can just note that P of 0 holds. And so this conditional, when n equals 0, will tell us that P of 1 holds. And then we can apply this again when n equals 1 and deduce that P of 2 holds, and so on. It's the and so on part that's not formal, that's very informal, so we need to do a better job of justifying induction before we use it. To justify it formally is not that difficult. All we have to do is appeal to the formal definition of the natural numbers. So specifically, consider the set S of all natural numbers n for which P of n holds. Then the set contains 0 because P of 0 holds. 0, of course, is the empty set, as we know. And part 2 here tells us that S is closed under successors. So S is an inductive set. That's exactly what these two statements are telling us, that the set we're calling S of all natural numbers n for which P of n holds is an inductive set. Well, we know that the natural numbers are contained in every inductive set. So n is contained in S, but of course S is a set of natural numbers, so that's contained in n. In other words, S equals n. So P of n holds for every natural number. Let's look at an example. Suppose we wish to prove that n is less than 2 to the n for all integers n greater than or equal to 0. Just to be clear, this is infinitely many inequalities, so we cannot prove this by plugging in values for n. We can plug in some small values to see if it's true. If we hit a value where it's false, we can stop, but that's never going to tell us whether this is true for all natural numbers. So we denote this inequality by the proposition P of n. To apply induction, we first have to check P of 0. P of 0 holds. 0 is less than 1. And as for the chain of conditional statements, we have to show that for all natural numbers n less than 2 to the n implies n plus 1 is less than 2 to the n plus 1. Okay, so we get to assume n is less than 2 to the n in order to show this. Well, if n is 0, this is true, so we don't have to worry. If n is bigger than or equal to 1, it's a very simple demonstration. N plus 1 is then less than or equal to 2n, because n is bigger than or equal to 1. And we can use the fact that n is less than 2n here to write that this is less than twice 2n, which is in fact 2 to the n plus 1. So n plus 1 is strictly less than 2 to the n plus 1, and we are done. So this set of conditionals holds for all natural numbers n, and so by induction we can conclude that P of n holds for all positive integers n, and in fact for all non-negative. So let me just say for all n bigger than or equal to 0. Okay. The technique of mathematical induction will also work for other starting points besides n equals 0. We may have a sequence of propositions P of n where n starts at 7 or negative 4. Just possible. So if m is any integer, positive, negative, 0, and if we want to establish that the propositions P of n are true for n bigger than or equal to m, that will follow if we can show these two facts. P of m holds, and the same conditional holds for all natural numbers n bigger than or equal to m. Actually, for all integers, I should say, because m could be negative. How do we justify this? Well, one way is to define new properties. Q of n is the property that P of n plus m holds. So Q of n holds means P of n plus m holds. So we've shifted the indices for the propositions so that instead of starting at m, they now start at 0. So this is for all n bigger than or equal to 0, which is the same as saying for all n plus m bigger than or equal to m. Then these two are equivalent to these two. Q of 0, which is equal to P of m. Q of 0 holds, and Q of n implies Q of n plus 1 for all n bigger than or equal to 0. This now is amenable to induction, so that if 1 and 2 hold, then 3 and 4 hold. In fact, that they're equivalent. And now we can apply induction to the propositions Q to deduce that Q of n holds for all n bigger than or equal to 0. In other words, P of n holds for all n bigger than or equal to m. Okay. So let's give the formal statement of the principle of mathematical induction. Let m be an integer. For each integer n bigger than or equal to m, let P of n be a proposition. If P of m holds, and if P of n implies P of n plus 1 holds for all n bigger than or equal to m, then P of n holds for all n bigger than or equal to m. I got a little break here I shouldn't have. This is often referred to as induction on n starting at m. N is the index for the propositions, so we say induction on n. It's a common phrase. And as indicated here, there's some important terminology here. The proof that P of m holds is called the basis step for the induction. And the proof that these conditionals hold is called the inductive step for the induction. Also, in order to prove one of these conditionals, you may assume P of n and show that P of n plus 1 holds. After all, if P of n is false, we know the antecedent is false, conditionals are always true. So all we have to contend with is the case when P of n is true to show that P of n plus 1 is true. The assumption that P of n is true for the purpose of showing P of n plus 1 is true is called the inductive hypothesis. Now, some students who were first introduced to induction often ask me, aren't we in the process of showing the inductive step actually assuming that P of n is true for all n bigger than or equal to m? Well, the answer is no. And you have to be careful here. What we are assuming is that a particular P of n is true only for the purpose of showing that P of n plus 1 is true. That's not the same as just a blanket assumption that P of n is true for all n, end of story. We make the assumption for a specific purpose. in order to prove a conditional statement is true, you're allowed to assume temporarily, let's say, that P is true in order to show that Q is true. Then after that's done, you no longer are assuming that P is true. You have deduced that the conditional is true. That doesn't mean that P has to be true. Okay? So that's something to think about if it's confusing. Let's take a look at another example of induction, this time involving a summation. We want to prove that these equations hold for all positive integers n. This is the sum of the integers from 1 to n is equal to n times n minus 1 over 2. A very useful formula, by the way, something that is probably worth remembering, or certainly putting it somewhere in your toolbox. In summation notation, it looks like this. To apply the method of induction on n, starting at n equals 1, we first check the basis step, P of 1. That is true. For the inductive step, we can assume P of n is true, so we get to assume this equation is true, but again, only for the purpose of showing that P of n plus 1 is true, which is this equation. Well, the rest is just algebra. Take this side here, I wrote it down here, and I included n here for a specific reason, because this portion now is the antecedent P of n, which we are assuming is true. So we get to replace the sum of 1 through n by n times n plus 1 over 2. That's the inductive hypothesis. And keep the n plus 1, do some algebra, and you get the right side here of P of n plus 1. So that's typically how an induction proof will work for summations like this. One thing that I should caution you about is, in the previous two examples, the basis step was all but trivial, and that often happens. And maybe for that reason, I sometimes will see an inductive proof where the author forgot to check the basis step. Oh, it's probably true. It's probably trivial. If you don't explicitly check the basis step and then write something down for the rest of us to see, you do not have a valid proof. It is possible, I have seen this happen many times, that the inductive step is mathematically correct, but that the basis step does not hold. So if you forget to check the basis step, it looks like you have a valid inductive proof, when in fact you have what we mathematicians refer to technically as garbage. Without the basis step, you can't get the chain started. So even if the chain works farther down the road, if you can't start it, you don't have a valid chain. Here's another, and there are times also, by the way, when the basis step is far from trivial. In fact, it can be a sticking point. You can say, well, this looks like it should be provable by induction, but you are unable to prove the basis step, even if you change the starting point. That's a tip-off that maybe what you're trying to prove is not correct. Okay? Or at the very least, you'll have to find some other proof technique. Let's look at another example involving summations. 1 times 2 plus 2 times 3 plus 3 times 4 and so on up to n times n plus 1 is equal to this. Maybe I should mention here, you can see from the previous example, what induction does is prove a given formula is true. It doesn't tell us, for example, suppose we have this and we want to know, is there a simple formula for that? Induction's not going to help. We're going to have to find some other way to produce the right side here. And then we can use induction to verify that our guess is correct. So that's what you might call a shortcoming of induction. And in fact, I often tell students, and it's essentially because of this, that inductive proofs are not very enlightening. They work sometimes and they're very powerful, but they don't always enlighten you as to what's going on underneath the surface. Anyway, once we have this formula, we can use induction to verify it. This is for n bigger than or equal to 1. So, in summation notation, the formula looks like this. First, we have to establish the basis step, p of 1, which is this, or equivalently this, and again, that's pretty obviously true. Just do the arithmetic. For the inductive step, we get to assume that this equation holds, p of n. It's the inductive hypothesis, and we have to prove that p of n plus 1 holds. Pattern is the same as it was in the previous example. We take the sum on the left side here of p of n plus 1. We split off the final term so that the rest of it is in fact the left side of p of n. You know, when you're trying to prove p of n plus 1, you're usually, assuming p of n, you're usually going to need p of n. And so you're going to need to you're going to have to try to manipulate p of n plus 1 so you can spot p of n. And that's exactly what we did here. We pulled off the last term so we could spot something relevant to p of n. Now we can replace this in the square brackets by this expression, and the rest is algebra. And we come to this side. If we came to something else that was not equal to this, we would know something was wrong. Probably the formula is not correct. Here's an example involving the product formula. The product from I equals 2 to n of 1 minus 1 over I squared is equal to this. Kind of a beautiful formula, actually. We can prove this for n bigger than or equal to 2 by induction on n. The basis step is p of 2, which is true. And assuming that p of n is true, we start with the left side of p of n plus 1. So this is the product up to n plus 1. Instead of breaking off the last term, we break off the last factor. And so this, in the square brackets, is the left side of p of n, so we can replace it by the right side of p of n. Still have to maintain this factor. More algebra, and we get the right side of p of n plus 1. Induction works on other things besides sums. We've already seen that in the first example of an inequality. Here is another example of the use of mathematical induction. Any set of size n has 2 to the n subsets. Or put another way, the power set P of S if S is a set of size n that has size 2 to the n. Any set, I better put an S in here. Sorry for the little peccadillos. There are several ways to prove this, and we're going to use a different technique to prove this when we talk about counting techniques later in the course. But for now, this is amenable to induction. So for all n bigger than or equal to 0, let P of n be the proposition that any set of size n has 2 to the n subsets. The basis step, n equals 0. Any set of size 0 has 2 to the 0, or 1 subset. This is true because the only set of size 0 is the empty set, and it has exactly 1 subset, namely itself. For the inductive step, we assume that P of n is true and show that P of n plus 1 is true. So here's a set of size n plus 1. We have to show it has 2 to the n plus 1 subsets. As always, we need a way to use the inductive hypothesis. So we need to find a set of size n to which P of n applies. Well, that's no problem. Just ignore xn plus 1, we'll have a set of size n. So what we want to do is split or classify the subsets of S into one of two groups. Those subsets that contain xn plus 1 and those that do not contain xn plus 1. The subsets of S that do not contain xn plus 1 are the same as the subsets of this set I called S prime. It's S without xn plus 1, so it's the elements x1 through xn. There's no difference between a subset of S that does not contain xn plus 1 and a subset of S prime. They're the same. But this has size n, so we know there are 2 to the n subsets of this type. In other words, 2 to the n subsets of S that do not contain xn plus 1. What about the subsets of S that do contain xn plus 1? Well, they are in one-to-one correspondence with the subsets of S prime, because we can take a subset of S that does contain xn plus 1 and throw out xn plus 1, we'll get a subset of S prime. And vice versa. If we start with a subset of S prime and toss in xn plus 1, we'll get a subset of S that does contain xn plus 1. So there's a perfect matching there, which means the number of subsets of S that do contain xn plus 1 is equal to the number of subsets of S that do not contain xn plus 1. And so that's another 2 to the n. So the total number of subsets of S is 2 to the n plus 2 to the n, which is 2 to the n plus 1. That's what we wanted to show. And so this so Pn plus 1 is true, and therefore the proof by induction is complete. If that was a little vague to you, I suggest you ponder this. This is an important argument worth seeing clearly. What you could do is you could take a set of size 3, for example, say the set, just a simple set like S equals 1, 2, 3, and look at the subsets of S that contain 3 and the subsets of S that don't contain 3, put them in a list, 2 columns, and compare them, and you'll see immediately what's going on. That's a common technique, by the way. If I'm trying to understand something that I'm not very clear on, I will very quickly say, well, maybe I better write down some simple cases. And oftentimes 2 or 3 simple cases, and I say, aha, so that's what's going on. And that's a very useful technique to have. You shouldn't be ashamed to write down simple cases and see if you can figure out what's going on. They never form a proof of anything, but they can guide you to an understanding of what's going on, and then you can construct a proof. Here's another example of induction. We can generalize many laws of arithmetic, set theory, for example, De Morgan's laws. This is one of the 2 De Morgan's laws for sets, generalized from 2 sets to multiple sets. The complement of the union of n different sets is equal to the intersection of their complements. So when n equals 2, this is one of De Morgan's laws, and we know it's true because I guess we proved it, or I asked you to prove it. I don't remember. So to prove this by induction on n, for n bigger than or equal to 2, we'll let P of n be the proposition that this equation holds. The basis step is true because, as I just said, when n equals 2, it's just the De Morgan law that we're familiar with and we know is true. For the inductive step, we assume that P of n is true, and we have to show P of n plus 1 is true. So here is the complement of the union of n plus 1 sets. But we can split this union by taking the union of a1 through an, and then taking the union of that with an plus 1. Think of this in square brackets as one set, which it is. Now, De Morgan's law for 2 sets applies, and this is equal to the intersection of the 2 complements. Now we can apply the inductive hypothesis, because now we have the union of n sets, its complement, that's equal to the intersection of the complements, and then we tack on the intersection of the final complement. So Pn plus 1 also holds, and that completes the proof.